Hey guys, my name is Danny Zuniga and I am participating in Challenge. So today I'm going to be helping you guys out with a little related rates problem. Here the problem reads: the volume V of a sphere of radius r is given by the formula V equals 4/3 power cubed. The spherical balloon is being filled by an incompressible gas at a rate of 25 cubic inches per second. How fast is the radius of the balloon changing when r is 18 inches? So basically this is a related rates problem, and it starts off by giving you just what the volume of a sphere is, the formula, and it's 4/3 power cubed. Then it goes on to tell you the rate at which this balloon is being inflated, and then it tells you that at this certain point of time, what that they're talking about, the balloon has reached a radius of 18 inches. So that's what I symbolize here in my little drawing of a balloon. You can see like the little balloon area and then like the little squiggly for the string. So you can think of this balloon as still being inflated, and so that's what I symbolize with the arrows, because they did tell us that it's being filled, which is a key word, filled by an incompressible gas. And so from there I go on to list my given information, which was that the rate dV dt basically means the rate at which the volume is increasing. So it's basically a derivative of the volume with respect to time, and derivative is almost synonymous with rate of change. They mean about the same thing. So there we got the 25 inches cubed per second, and then we also have the volume formula for a sphere, which is 4/3 power cubed. Now if you look at this work, you might be saying, oh my gosh, Danny, what are we doing here? But bear with me, guys. So we already went through dV dt is the rate at which the volume is changing, and we also know the volume formula. So to use that information, we're gonna have to take the derivative of the volume, as I did in this step right here. So what I'm doing here is taking the derivative of the volume up here. So with respect to time, of course, because time is the variable here when inflating the balloon. So to take the derivative, we just simply put, say v, since it is a variable, we just put dv over dt. And then here we have 4/3 pi r cubed. And 4/3 pi can be thought of as a single number because it is a constant and it doesn't change, so it's not a variable. So we won't be taking the derivative of that, so we just bring that down, 4/3 pi. And then our variable is r here, and we are taking the derivative with respect to t. So real quick, if you guys look here, you'll see that what I did was bring the power to the front of the r, so 3r, as you can see here. Ignore the crossed out, we'll get to that later. And then you subtract 1 from the power, so now it's squared. So you just bring that 3 forward and subtract 1 at the top, so now it's 2. And then you have to place that dr dt there, and I'll explain that right here in this little side example. So basically, you think of r cubed. It's a big difference to say a derivative with respect to r than a derivative with respect to t, especially like in this problem, because that's what we're looking for. So the derivative with respect to r of r cubed is just the 3r squared, as we talked about. You move it to the front, and then you take away 1 from the power to get 3r squared, I'm sorry. And then if you want to take derivative with respect to a different variable, such as t in this case, then you would have to add that dr dt. And the reason being that the rule states that you must first do the power rule and bring the 3 to the front and then subtract 1, as we did here. And then you must take the derivative of the variable inside, which is r, with respect to the time. So the way to do that is to write the dr dt. So now back to this example, you can see why we did the dr dt, because we needed to know also the derivative of the radius with respect to time. Now back to the problem here. So now we have everything set up, we have everything we need, and now all that's left is to plug in the values. So we know that the derivative of volume with respect to time, as here, is 25, so I just placed that number in right here. Now the units, it's not that important right now, we'll get back to that at the end. And so here's the 25, and then as you can see on the top right here, the 4/3 and the 3, it's a denominator and numerator, so they cancel out. And so now I'm just left with that 4 and the pi, and then 18 is instead of r because the radius was told to us to be 18 inches. So now I put an 18 instead of that r, and then I keep that drdt because it's still a variable. So now you guys can see we only have one variable, so by algebraic methods we're gonna solve for that one variable. So we're just going to divide by the 4 pi times 18 squared on both sides, as you can see I did here. And then this cancels out, so now we're just left with the drdt equals 6.14 times 10 to the negative third inches per second. And so basically that's drdt is saying the derivative of r with respect to time, and as we covered before, derivative also means rate of change. So what we're really saying, if you want to say this out in words, it's that the radius is changing at a rate of 6.14 times 10 to the negative third inches per second at the time at which the balloon has a radius of 18 inches. So guys, I want to thank you guys for watching my video, and I hope this cleared up a few things. If you guys had any questions for the few that are going to watch this video, thanks a lot guys.